Welcome back. In module 10, we will cover transportation demand modeling using software. And in this particular lecture, we'll start with general transportation software. So we will talk about the background of transportation softwares, and then we will look into macroscopic transportation demand models and microscopic traffic simulation models. So basically, with the shift of modeling, transportation modeling from aggregate to disaggregate modeling, the data requirement has increased tremendously, and not only that, to manage the traffic, the trips or the tours for different groups of people belonging to different socioeconomic backgrounds, and then looking into different trip distribution models, and then again distributing that models as per different modes. This is a huge amount of data that needs to be handled, and it is very difficult for an individual to do all these models in stages. And if I want to do it for a few zones, it is fine. But if I want to do it for a larger area or a region, then it is very difficult to handle this kind of work without the help of any softwares. So that is why we require transportation softwares which are able to handle large areas, and it can also handle at different levels of details. Like for example, we can go for like macroscopic models or mesoscopic models or microscopic models, and this actually helps us to put in the appropriate amount of details for each kind of model. So if I want to develop a macroscopic model, there is no need to put in intersection geometry for the links in that particular model. So accordingly, this macroscopic model will require a different set of data, whereas a mesoscopic model will require another set of data. So according to the model details that we are trying to develop, so we will build a particular model, and so the total we will categorize the total transportation software into these three kinds, but most of the commercial software available can handle all these kind of models. So some of the commercial software available are Cube and Visim. These are the two primary softwares used all over the world, and as you can see that I have categorized them under three categories, three types of software categories, like transportation planning, traffic simulation, and emission modeling. So you can understand when we are talking about transportation modeling, we are talking about overall travel demand management, including freight management. And when we are talking about traffic simulation, we are looking at the microscopic level study, where we are looking into movement of vehicles in each corridor and what kind of effects it is having at different times of the day, what kind of congestions, queues are being generated. So that is all about traffic. That is why we need to do traffic simulation. So these are two different levels of model, and each like a Cube along with its different components can handle both transport planning as well as traffic simulation. And also most of the travel demand models also have got a supporting emission modeling which actually could be undertaken. Like for example, for this kind of vehicular flow, what kind of emissions are generated. So for that, Cube has got Cube Dynasim, which is the traffic simulation component, as well as the PP suite, which could be used for emission modeling. Whereas Visim has got Visim for the traffic simulation component, and then for emission modeling we can also use Visim as well. So then in addition to that, we have also discussed these models like UrbanSim, EmiPlan, then TransCAD, EMI2. This we have discussed earlier when we were discussing overall land use transportation model models earlier. So these are some of the models which are popularly used all over the world. So out of all this, and you can see that most of them has got a transport planning component as well as a traffic simulation component. For example, UrbanSim has got RouteSim as the traffic simulation component, and it has also a emission modeling component, which is Cal3QHC. So this is the different kind of software which are available, which people commonly use to do travel demand modeling. And out of this, over in this particular lecture, we will talk about both Cube and Visim, because these are commercially available software. And as you can understand, when it is commercially formulated, these are more robust softwares. But at the same time, these softwares could be the calibration, the amount of calibration that we can do is to some extent limited, because these are commercially available softwares, but the amount of data it can handle, the way all the different the different kinds of components that are required to run this kind of models, these are all present in this particular software suites. So, when we talk about these three levels of models, one is macroscopic, then mesoscopic and microscopic. So, we can understand macroscopic models are for larger areas or for big groups of population. So, these are primarily used for either 4-stage model or for generating an activity based model for an urban area. So, that means these are the models which are usually used for this travel demand modeling part. So, this could be and as you understand, as we have already learned, that there is travel demand and there is also the question of supply, and that is why we have our traffic assignment models, which actually assigns the demand that is generated to the different networks, and then a feedback from the network comes which actually influences the demand as well. So, so the next part of the model, so it can not only handle large areas in forms of zones or TSZs and so on, it could be also used to model the entire network. So, it is used for network planning, and eventually it is used for regional level travel demand modeling as well. And this kind of models can implement traffic flow, density and speed values to a network characterized by accurate distances, geographic locations and capacities. So, first we have to build the network within these models, and once the network is built, then we have to determine based on the demand what kind of traffic flow, density and speed would be generated in this particular network. So, you have seen that in the bigger large macroscopic model, we do not go into simulation of the traffic signals as well. We cannot usually undertake this dynamic traffic assignment. We will stick to link cost function. So, that is why this traffic flow, density, speed, these are the things, parameters which are associated with the network when we do macroscopic models. And of course, the computer complexity of this kind of work is low, and it is not suitable for simulating transport incidents, road geometry, impact. So, this microscopic level thing is not done in this level of models. And some of the examples are the Cube Voyager. This is the component of Voyager which component of Cube which actually handles the 4-stage models or a tour based model or activity based travel demand models, and same goes for PTV Visum and Transguide as well. So, these are the softwares which can handle this kind of models. So, when we talk about a mesoscopic model, it is a bridge between the microscopic and the macroscopic models. So, these are the models which can actually help us to do dynamic traffic assignment. So, microscopic model is even further details. That means we can actually simulate the queue lengths and what kind of situation is there in that particular queue, what kind of like for example, when every vehicle could be modeled in a microscopic simulation. But in a mesoscopic model, we cannot model every vehicle, but at the same time we can generate the total amount of signal time, the turn volumes, the total amount of queue lengths. So, this could be done at the mesoscopic level. So, if you want to run a dynamic assignment model, in that case we need to probably have, along with macroscopic model, either we can go for microscopic model of course, but microscopic models are very data intensive and it takes a lot of time to simulate traffic for a particular area. So, we cannot apply that to the entire city at one go. We can model it for a particular small zone. So, that is the amount of complexity these models can handle. But a mesoscopic model is somewhere in between. It can get us the details which is required for dynamic traffic assignment, and like how the link, how the queues increase with increasing demand, increasing amount of vehicles coming into the link, and then how when the link the total amount of vehicles falls down in the link, gradually the queue dissipates, and how the queue is moved to the next link. So, all this how the congestion spills over to the next link, all this could be modeled using the mesoscopic models. So, it is capable of simulating impacts of traffic incidents and accidents, but not at very detailed level. So, it can generate some impedance or it can add it can model the time, increase in time of course, but it cannot do it in that much details. So, the two components that we use are Cube Avenue and TransSims. These are two examples of mesoscopic models. So, mesoscopic simulation is available in both Vissim and Visum as well. So, then comes to the microscopic model. There we simulate small independent areas of population. That means we cannot do for a large city. We take up a CBD or even a smaller area in a CBD, and it represents detailed behavior of individual vehicle movement. So, every vehicle, how it is getting inside the link. So, there is a arrival function. There are different functions that are used, maybe exponential, maybe following normal distribution, or that based on that, the arrival rate of a particular vehicle, we actually include that vehicle in that particular link, and then we simulate its flow. So, it follows another vehicle, and then it can also change lanes in a particular road or a link. So, this kind of behavior is actually modeled. So, two main things that are modeled is we implement individual driver behavior associated with lane changing, reaction time, and the car following model. So, this is how a movement of a vehicle is modeled. So, how it is following a car, how it reacts to that particular car when it does something, then about the lateral movement, like the lane changing, when it changes lanes from one side to another, how it does, what are the rules it follows. So, this kind of, there are certain rules for that. So, this kind of things could be modeled, and we can, and when this is done in a simulation with certain time intervals, it is like it's a discrete interval, or it could be done in a continuous way, and then once it is done, it can automatically generate what will be the situation in that particular link. So, usually why it is done like this? Because it is very, very difficult to model all this behavior using mathematical equations. So, when we do simulations, automatically the vehicles interact with other vehicles, and also it interacts with the different road geometry, and accordingly the resulting outcome is the solution. So, it is too complex to be modeled using now standard equations. So, that is why we will go for this microscopic simulation. So, it accurately simulates the impact of transport incidents and network restrictions, and computer complexity is high. And for examples, a Cube DynaSim, then PTV VSim, MatSim, CoreSim, these are the different simulation softwares that we use. So, when we talk about macroscopic travel demand models, Cube Voyager and PTV VSim are the most popular travel demand models. Cube Voyager also come with the Cube base. That means there is a base model. This is the model component for Cube, which help us to design the networks and so on. Whereas PTV VSim has inbuilt, that means it's a part, designing the network is part of PTV VSim itself. Whereas in Cube Voyager, we will do it as in Cube base, and then use it for Cube Voyager to actually do the travel demand modeling. So, these are the most popular travel demand models commercially available, and both are used for long range traffic demand forecasting, and it is also used for at different scales, that means or regions. It could be at the national level, it could be used at the state level, it could be used at a regional level, or it could be used at a metropolitan level. So, it could be used in different scales as well. So, what are the different things that could be done in this kind of software? We can do transport network mapping. So, the entire transport and the road and the transit network could be mapped using this kind of software. And this mapping is not actually mapping of the roads and all. This is mapping of the links, nodes, then the connector between different links, from which side you can go, which flows are allowed, which flows are not allowed. That means you can take a turn on the left side, but you cannot take a turn on the right side. So, all these things could be modeled. And then this is the transport network mapping. And then the travel demand modeling part, which we can use either aggregate models or disaggregate models. It could be a 4-stage model, it could be an activity based model. Then finally, once that basic travel demand is modeled, we can also do assignment procedures using different algorithms. So, there is support for different kinds of assignment. Then formulation, management and comparison of different scenarios. This is why we use this kind of software, because we can actually model the scenarios very fast. So, we have the basic model done for an urban area. and once the basic model is done, then we can change test certain policies. For example, there was a case like a few months back when the pollution level exceeded in many parts of the country, and there was policies, there were some recommendations like to test what is the effect of having an odd and even rule for passenger transport. For example, in one day you can cars having an odd number will be plying on the roads, in the other day even cars having a even number will ply on the roads. So how to model that? So we can actually model that also using this kind of software, and then immediately we would have seen what would have been the effect of this kind of policy. Or there could be a policy of a certain area is restricted for car use. That means if we change certain areas from one way to two way. So what kind of effect it will have, and if we restrict increase the parking, we restrict parking in a particular area, what impact it will have. So this kind of things could be immediately told. So the difference between the reason why we use software is to get these feedbacks just as soon as we set up the policy. We can do with minor changes, we can actually run the models and can get these results. So once we can run the different scenarios, we would be similar to that. We can also do data analysis, statistics. We can create reports for the management, whoever runs the transportation, or for the decision makers who could take decisions seeing this kind of reports. And now regarding this particular model system, this both static and dynamic traffic distribution could be modeled, and then network parameters could be modeled, and integration of geographic information system, of course, and user interface for script based system. Now this is how why we use scripts, because the standard models are there in the system. We can use those models directly, and that means, but if we want to calibrate those particular models, we have to, that means, modify some of the model equations, or rather we can modify the models as well. So that's why we need to use scripts. Scripts are smaller programs that are written in a language which is maybe only which may be a common language, like it could be a Python script, or it could be something which is very, very custom for that particular software. So the software sets its own rules and all, and instructions that to do a certain kind of change you need to write this command, and accordingly we will follow that, and we will write a sort of command which will update the existing model and before running it. So usually in transportation software we have to write these scripts to update the model structures. Then just on in the table we can actually just take a look. So we can compare a small comparison between Cube Voyager and PTV Visum. So over here we can see that the software suite is Cube, and the other one is the software suite is PTV Vision, and the Voyager is the one supporting this macroscopic model, and where Visum is the one from PTV which supports the macroscopic model. Dynasim is for simulation, Visum is for simulation over here, and Cube Land and Cube Vistro, this support the land use component. So when we are going to develop land use transportation part, we also require a component which talks about real estate development, what kind of and how the changes in the land use takes place. So that is taken up in Cube Land, and in PTV it is taken up in PTV Vistro. And then we also have got Cube Cargo, which could be also used for modeling freight transport as well. So just to compare between Cube Voyager and Visum, more or less all the different, as we can see in this particular table, it has a level of details is more or less. Cube Voyager is macroscopic, Visum could be both meso and macroscopic. It has got a nice graphical interface, both of them. It has got a user-friendly interface. It is integrated with GIS. We allow import and export of data. It could be travel forecasting could be done based on trips. It could do travel forecasting based on tours, as well as it could do travel forecasting based on activity-based modeling as well. Now, activity-based modeling we haven't yet covered. It will be taken up in the final module, module 12. So once you complete module 12, you can always visit the transportation software to see how we have we could do this. You can revisit this module, and you can learn about how activity based modeling could have been implemented in this particular software. So, we can also have programming language extensions. This is talking about the scripts, and then interface with other software packages, that is possible. Traffic assignment problem, there are some changes between Cube Voyager and Visum. Like for example, Cube Voyager does path based assignment using gradient projection method. By conjugate Frank-Wolf usual equilibrium assignment is undertaken, whereas in Visum path based equilibrium and Loche and a variant of Frank-Wolf is actually utilized. So, in Cube Voyager, the network model is constructed using different layer based trajectories or links, and these links are drawn using a background map or aerial photograph as a reference. That means we can import a background map, and over that we can actually draw the links, and then we can modify the links and adjust the links, and each link has specific attributes and must be assigned to a particular layer. And we have got different formats of input data which is supported, like for example, we can load zonal data, we can have record data, we can load matrices, we can have network data, geo databases and GIS shapefiles. All these things could be used as input data. And possibility to, we can also model any mode of transport. For example, we can model slow modes, walk and biking, bicycling, both could be also done in Cube Voyager. So, earlier these were not included, but now we can model slow modes as well. So, PTV Visum network is created using links, and we use something called connectors as well to say that how different links are connected, which turns are allowed and so on. And the composed and it is composed of layers of different object classes. So, each kind of item is a class. Like programming, in program we use the concept of class, and in Visum also background map or aerial photo is required to draw links and connectors, same as Cube Voyager, and links are assigned with the attributes such as speed, number of lanes, lane width and so on. So, all the link characteristics are given in both the softwares of course, and it integrates all relevant modes of transportation. So, they can allow cars, we can model cars, we can model car passengers, goods, vehicles, bus, train, motorcycles, bicycle, pedestrians in a unified network data model. So, it is in one model we can implement all these particular modes. Can model, so something new in PTV Visum is they can also model ride sourcing services as well, and mobility as a service, MaaS with autonomous vehicles, that also could be modeled using PTV Visum. So, this is something new. Now, now that we have discussed the macroscopic model, in microscopic traffic simulation models, again this is another part when we do transportation modeling or when we use this kind of softwares. Primarily these are focused, one part is the macroscopic part, mesoscopic is somewhere in middle, but more or less it is connected with the macroscopic part. But microscopic is a bit different, and we use microscopic traffic modeling for modeling certain kinds of traffic geometries, that if that what would be the impact of that particular geometry, or we can model certain kind of traffic signal systems and many other things. So, it is like we have already discussed, Cube DynaSim and PTV Visum are both traffic simulation models. So, these are the two models from this two Cube and PTV group, and then where these are applied, these are applied in traffic engineering studies. We can do parking simulation studies, we can do pedestrian simulation studies. For example, if we have a large facility, when there is a like a stadium, when there is a break, that means when the game ends, how when people are coming out, where they will go, and where they will once they come out, that how they will gather at different transit stops. All this could be also modeled. Then signal optimization of a particular corridor, and public transport operations planning, and fare analysis for public transport or toll roads. All this could be modeled using microscopic traffic simulation. So, now looking at DynaSim from Cube, it is of course microscopic model, and it could do event based simulation as well, and it is also stochastic. That means there is we can apply probability models to determine what would be the effect of based on probability of certain things. We can also do the entire modeling. So this stochasticity is also allowed in DynaSim. Driver behavior parameters are categorized into two main categories: lane changing parameters and car following parameters. So as I explained earlier, that is when a car is introduced into a particular link, that means there is an arrival function to initiate the movement of the car, and then the car follows another car. So there is car following, and then the car can also move laterally on two sides, and then there is lane changing as well. So this two behavior has to be modeled, and there are certain set of rules that has to be followed to model this kind of behavior. So that is actually determined, and vehicle interactions are based on priority rules only, and DynaSim can be also integrated with Voyager. So that means these are all integrated models. That means DynaSim as well as Voyager, these are all parts of Cube. So this could be of course integrated. So when we talk about microscopic in VSIM, of course it is also stochastic, dynamic microscopic simulation software, and it covers all modes of transportation, and it can analyze their interactions. So that is same in VSIM as well, same capabilities. VSIM also requires driver behavior parameters assignment to obtain accurate simulation. It could be divided into four categories: car following behavior, lane changing behavior, these two we have talked, then lateral behavior, lateral movement along, and then signal control is also there. And VSIM implements how in a signal what happens and how it behaves. So that is also could be done. And then VSIM can implement longitudinal vehicular movement using psychophysical car following model. So that means not only the physical characteristics of acceleration or speed, distance, and all these things are maintained, but also the behavioral part for the driver, that all these things also is modeled in the this particular kind of system. And then lateral vehicular movement is based on rule based algorithms, and vehicle interactions are based on priority rules, conflict areas, and signal heads. So these are three different ways the vehicles interact at different situations. So VSIM can be integrated with VSUM. For example, travel demand volumes can be estimated in VSUM and then exported to VSIM for microscopic simulation. So once we have done the overall travel demand estimate, we can actually simulate what would be the effect in certain areas, because we cannot model too large area. So that could be done. And this uses a link connector system to map networks, allowing flexibility to evaluate complex intersections and roadway transit networks. So as I explained earlier, it is not only links and node, it also allows this. It has also another parameter called connectors, which tells us how the different turning volumes and what proportion of vehicles turns in which direction, and all these things could be modeled as well. So this allows complex interactions that could be modeled in a particular intersection, and then also we can do the same for transit networks as well. It is also possible to simulate ride sourcing and mass autonomous vehicles, so that we just discussed earlier. So the different level of details for the microscopic traffic simulation models, again more or less both the Cube and VSIM are similar, show similar amount of capabilities. Level of detail, user friendly, graphical interface is nice, GIS integration, import export allowed, pedestrian movement allowed, bicycle motorbikes could be modeled, parking simulation could be done, ITS components could be also inbuilt, also modeled along with this. Then autonomous vehicle modeling and mass modeling, this is only possible in VSIM. Now, what kind of data is required for this microscopic models? We require data on roads and number of lanes, this kind of data, the link data, link-wise width, and all these things we can, other sort of data, then where it starts, where it ends, and all this. Then junction geometry, this we have to enter, then vehicle types flying on the road, the what kind of vehicles are there, the distribution that has to be entered, total number of vehicle counts that has to be entered, travel time and delay data, this has to be there, parking areas data, which areas we are allow parking, signal time, signal phasing, what we are planning, or we can also simulate, determine appropriate signal times and signal phases for each of the intersection based on the flows as well. So travel speed, we can also determine this, we have to also enter travel speed data, and if applicable, non-motorized transport infrastructure, pedestrian, cyclist count, public transport infrastructure could be also input into the data set, which could be used for modeling their movements. So these are some of the references you can study. So to conclude, the current shift in land use transportation models from aggregate to disaggregate modeling has made the use of transportation software mandatory due to the sheer volume of data required to calibrate and then implement these model systems. At present, there are multitude of state-of-art softwares available which can handle both macroscopic and microscopic level of details. And finally, use of transportation software can help us to quickly evaluate the effect of potential policies before implementation once the basic model for urban area is built. So this is why we require transportation software. And in the next lecture, we will get into in more details about the CUBE software and the different components of CUBE software. Thank you.